This is our third lecture on the design of structural steel connections. In our last lecture, we looked at the different actions and bolts that may come onto a bolt. We looked, for example, we saw that three types of actions may come onto a bolt. One is the bearing type actions, another is the shearing type action, and another is the tension forces. And based on these actions, we will be calculating the bolt capacity. So today we will look at the Codal provisions for calculation of bolt capacity, and as already discussed, we will be looking at IS 800 2007 code. So before going into the Codal provisions, we ended our last lecture with one question. I ended last lecture by posing one question here: which do we design first? Do we design a member first, or do we design a connection first? So obviously in most of the cases we design the member first, and based on the member forces we design the connection. For example, if you have to connect a beam and a column in this way, this is just an example. First we will design the column or beam. We will ascertain the member forces that are coming onto these structural members, and based on those member forces we will be designing the connection. So the general workflow is, first we will have the member forces, and based on the member forces means the forces that are coming onto those beams or columns. Based on these member forces we will determine the forces in our connection that we have to design. After getting the forces in connection, we will determine the number of bolts that are required for our connection. Number of bolts, because we are talking about bolts at present only. So to calculate the number of bolts from the forces and connection, we have to determine the bolt capacity. So this is what we will be dealing with today, this calculation of bolt capacity. So before going into this bolt capacity calculation, let me talk a little about two different types of bolts. One is the bearing type bolt, which we will be discussing today. The bolt capacity that we will be discussing today are for bearing type bolts, and another we have friction type bolts or friction grip bolts. So the calculation of bolt capacity for both of these types of bolts is given in IS 800 code. For today we will be discussing with bearing type bolts only. So what are the differences between these two types? The bearing type bolt we discussed in our previous lecture, or maybe the lecture before that, in which we saw an example where two plates were clamped together with the help of a bolt in this way, and bearing stresses and shearing stresses were acting on this bolt. When we discussed about single shear joint and double shear joint, we discussed. So these are the normal type bolts, which are bearing type bolts. Now in contrast, what are these friction grip bolts? For example, let us say that again we have the same condition. We have two plates which are being connected by a bolt here, but now instead of the bearing forces or the bearing stresses that may occur in this first type of joint, what we do is we apply some pre-tension to this bolt here. And how are these pre-tension applied? They are applied with some kind of torque wrenches. You can look into Google and see what are these wrenches. Using these wrenches we apply some pre-tension here, and after the application of pre-tension, what happens is that these surfaces of these two plates, they come into intense contact with each other. So this intense contact due to pre-tension, this causes the development of contact pressure, high contact pressure between these two plates, and this high contact pressure is responsible for the transfer of forces that is coming onto this connection. So this type of load transfer mechanism, we use a certain type of bolt for this type of load transfer mechanism, and these are called friction grip bolts. So in friction grip bolts, the load is transferred or resisted by the development of contact pressure between the plates. We do not talk about bearing in such cases. So these are the two types of bolts. Generally what happens is that because high amount of pre-tension is applied in these bolts, the type of bolts generally used for these friction grip bolts are high strength bolts. So we discussed 4.6 grade bolt is generally known as mild steel bolt, and then 6.6, 8.8 or 10.9, these are the high strength bolts. So generally high strength bolts are used for friction grip bolts. Now after knowing this, now let us go into the let's go into the capacity calculation of bolts. So we will be discussing with bearing type bolts, and the capacity calculation for bearing type bolts is presented in section 10.3. This is clause 10.3 of section 10 in our IS code. So we know that three types of actions occur on a bolt: bearing action, shearing action, and tension forces. So first we are going to see the shear capacity of bolt. How do you determine the shear capacity of bolt? So let's see here, as given in the code, the design shear strength of bolt. The design shear strength of bolt is given as the nominal shear strength of bolt divided by the partial safety factor gamma mb. For the partial safety factor, you can see table 5 of IS 800. So we will not go into this today. We will look at the partial safety factor in our next lecture when we will perform a numerical for the calculation of bolt capacity. So the design shear strength of bolt is given by the nominal shear strength of bolt divided by the partial safety factor. So how is this nominal shear strength calculated? Is given here. Nominal shear strength of bolt is given as the ultimate tensile strength of bolt divided by root over 3. We have something as NN ANB plus NS ASB. So this Fu by root 3 generally represents the permissible shear stress in a bolt. So the nominal shear strength of bolt is, we have this permissible shear stress. Now to determine the nominal strength, we have to multiply this stress by some value of area to get the force. So this term inside the bracket is our area. So what does this NN and NS represent? Remember in our previous lecture when we were discussing about this bolt forces here, bearing forces and shearing forces, we said that in these surfaces where the bearing forces are generated, or in this surface where the shearing forces or shear plane lies, these planes may or may not be in the threaded portion, or may or may not be in the sank portion. For example, if this is our bolt, this is the sank portion and there will be threaded portion at the bottom. So the shearing planes and the bearing planes, for now let us consider only the shearing plane since we are considering or discussing about the shear capacity of bolt. This shearing plane, it may even lie in the sank portion, or this may even lie in the threaded portion. So this NN represents the number of shear planes with threads intercepting the shear plane. That means this is the number of shear planes lying in threaded portion, and NS is the number of shear planes lying in the sank portion where there are no threads. And A and B, this is the net shear area of the bolt at threads, and ASB, this is the nominal plane sank area of the bolt. So we can determine the value of NN and NS by looking at whether our joint is a single shear joint or double shear joint. So if it is a single shear joint, what happens is that first, for this how we will proceed is, generally the critical portion or the critical condition is one in which the shear plane lies in the threaded portion. The critical condition is 1 for which shear plane lies in the threaded portion. So if we have a single shear joint, what we will do is we will consider, for conservative calculation, to be on the safe side, what we will do is we will consider this NS. That means the number of shear planes lying in the shank portion is 0, and we will take the value of NN is 1 here. So that we do to be on the conservative side, to be on the safer side. And how do we calculate this area here? ASB, this is the area of the shank area. We know we can do this as pi by 4 into the diameter of the bolt whole square. And for A and B, that means the area at the threaded portion, what we generally do is we can take is 7.08 to 0.78 to 0.8 times the shank area. So we generally take this 0.78 into ASB. Now you can see why the critical condition is for the shear plane lying in the threaded portion, because the area of the threaded portion is less as compared to the area of the shank portion. When we consider that the plane lies in the threaded portion, this value of area, this value that is inside the bracket, we will get lesser area, so that the nominal shear capacity of the bolt also comes out to be a lesser value. So that is why for single shear joint we will consider the shear plane to be lying in the threaded portion to be on the safer side. For double shear joint, we can take NN1 and NS1, and then we can perform calculation. So we will look at this calculation in our next lecture, when we will discuss this formula in detail once again. So this is about the calculation of shear capacity of bolt, and you can see that for the calculation of shear capacity of bolt, the only thing that is playing a role here is the cross-sectional area of the bolt. Of course, we have this ultimate tensile strength of bolt, but the geometrical parameters that is affecting the shear capacity calculation is only the cross-sectional area of bolt or the dimensions of bolt. But if we look at the bearing capacity of plate or bearing capacity of bolt, that is not the case here. Let's see. Since what we discussed in our last lecture was that bearing is a two-way process. That means the bolt is also bearing on the plate and the plate is also bearing on the bolt. So bearing is a two-way process, and hence the capacity of bolt on bearing is affected by the dimensions of both bolt and plates here. So now let's see here, the design bearing strength of bolt is again in the same way the nominal bearing strength of bolt divided by the partial safety factor. The nominal shearing strength of bolt, this is given by this formula here, 2.5 kV dt Fu. Here kV is the smaller of these four values here. kV is the minimum of E over 3d naught, P over 3d naught minus 0.25, FUV over FU, and 1. kV is the minimum of these values. This D represents the diameter of the bolt. This D represents the nominal diameter of the bolt. Remember and don't be confused. D represents the nominal diameter of the bolt, but this D naught represents the diameter of the hole for that bolt. So D represents the nominal diameter of the bolt. FU, this is the value for FU is, you have to take the smaller value of either FU for bolts or FU for plates. Whichever is smaller, the ultimate tensile stress of either the bolt or the plates, you have to take the smaller value of FU here. Now T means, let's see here, T is the summation of the thickness of the connected plates experiencing bearing stress in the same direction. So now let us understand what T is by taking the same figures, same single shear and double shear connection that we have been discussing till now. For example, let's see here. Here I have drawn the same diagram here. this bolt is in single shear, whereas the bolt in this second diagram, this bolt is in double shear here. So the forces are acting in left hand side for these plates and on the right hand side for this plate. So let us say that the thickness of this plate is T1 here, the thickness of this plate is T2. Similarly, the thickness of this plate is T1, middle plate T2 and T3. So now let's see for first case here and second case. Let's see for first case. So T, we have the summation of thicknesses of the connected plates experiencing bearing stress in the same direction. Now we know that for this single shear joint, for example, for the upper plate, the bearing forces are being generated on this plane, and for the lower plate, the bearing forces are being generated on this plane here. So the bearing stresses are being generated in the opposite planes or in the opposite directions for this single shear case. So the value of T will be the minimum of T1 and T2. Whichever is smaller, we have to take minimum T1 and T2. But the opposite case here is, in this double shear joint, for the upper plate, this is the bearing stress direction. For the middle plate, the bearing stresses are generated here, and for the third plate, the bearing stresses are generated here. So now you can see that the bearing stresses are in one direction for this second plate and in another direction for this first and third plate. So for this case, the value of T will be the summation of plate thickness in the other direction. This is T1 plus T3, because for the first and third plate, for the upper and lower plate, the bearing stresses are in the same direction. So this is how you determine T. Now we know how to determine D. This is just the nominal diameter of bolt. T, this is about thickness, and Fu. So what is kV? kV you can see here, E over 3D naught, P over 3D naught minus 0.25, FUB over FU, and 1. kV has 4 probable values, and out of these 4 probable values, we will take the minimum one. So what is this E here? E is the end distance, D naught is the diameter of the hole, P is the pitch distance, again D naught is the diameter of the hole, FUB is the ultimate tensile stress of the bolt, Fu is the ultimate tensile stress of the plate. This ultimate tensile stress will be known based on the grade of the material that we have selected, and 1, we have 1 here. So let's discuss a little about this E, P and other things. For example, okay, let us see a plate which has more than one line of bolts. For example, since one bolt may not be sufficient always to connect the plates, let us see one plate with multiple line of bolts. 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Let us say that, or let us consider that the forces are being acted in this direction here. So now the distance between these two consecutive bolts in the direction of the force, we call this distance as pitch distance, which is represented by P. And the minimum value of this pitch distance as given in your code is, the minimum value is 2.5 times the bolt diameter. This is the minimum value of the pitch distance. So you can see about, or you can see the clauses about these distances probably in 10.2.2, 10.2.3 and 10.2.4. Please go through in detail by yourself. I will just be discussing some values here. So the pitch distance, the minimum value is given as 2.5 times the bolt distance. Similarly, in the other direction, this is known as the gauge distance. So this is about the center to center distance between the bolts. What is the distance between the center of this hole and the edge of this plate called? either this distance or you may also consider this distance here. What are these two distances called? So if we consider the distance from the center of the bolt to the adjacent edge of the plate in the same direction of the force, that means the force is acting here in this direction. So if we also consider the distance in the same direction as the force is acting, this distance is known as end distance. So if the distance from the center of a bolt to the adjacent edge is in the direction of the stresses or in the direction of the force, we call that as end distance. But if we are looking at the distance from the center of the bolt to this edge of the plate in a direction at right angles to the forces, the forces are acting in this direction here, but now we are looking at the distance in this direction. So if this direction is taken to the right angles of the forces or to the right angles of the stresses, this we call as edge distance. So both edge distance and end distance, the minimum value of edge distance or end distance is generally taken as 1.5 times the now hole diameter. Now it is not bolt diameter, but it is the hole diameter. So these are for machine cut edges, and we generally consider machine cut edges. If those are hand cut, then we take as 1.7 times the hole diameter, but for now we will take as 1.5 times the hole diameter. So this is about edge distance and end distance and their minimum value. So for more detail on these distances, please look through these clauses in IS 800 code. So now we have determined kV also. We have determined all these four values here, and after determining those values, we can calculate the nominal bearing strength of bolt, and using that we can calculate the design bearing strength of bolt. Now finally, after shear capacity and bearing capacity, we look at tension capacity of bolt. Tension capacity of bolt is presented in clause 10.3.5. Again, a bolt subjected to a factored tensile force TB should satisfy this condition. That means always the design strength of bolt should be greater than or equal to the actual forces coming onto the bolt. So this TDB, design bolt capacity, is again calculated in a similar way, the nominal bolt capacity divided by the partial safety factor. We are using the partial safety factor because our design is based on the limit state theory. So remember that everywhere we have partial safety factor. So TDB is TNB by partial safety factor. How to calculate this nominal capacity of bolt? The nominal capacity of bolt is given here is 0.90 FUB over AN, which should be less than FYB ASB, okay, into gamma MB by gamma M naught. So you can see two conditions here. One is this condition and one is this condition. So what are actually these? Why these both needs to be checked? So the first 0.90 FUB over AN, this represents the limit state governed by the breaking of bolt, whereas the second formula, this is the limit state governed by yielding of bolt. So based on both of these limit states, we have to calculate the nominal bolt capacity for tension, and whichever value is less, we have to adopt that. You may have heard this limit state governed by breaking of bolt is about the rupture of net section. And this limit state governed by yielding of bolt, we generally call it yielding of cross section. So on the application of tension forces to our bolt may either break at a certain point. This cross section decreases as we apply tension forces on our bolt, and at a certain point our bolt may break, or instead of breaking there might be yielding of the section. So both of these limit state governs the design of our bolt. We have to calculate the nominal capacity based on both of these limit states, and we have to take the smaller value of these two forces, and based on that now we can calculate the design strength of bolt. So this is about calculating the tension capacity of bearing type bolts. So what we have discussed today, we have discussed it about the calculation of the shear capacity of bolt, the bearing capacity of bolt, and the tension capacity of bolt. Whichever value comes less, that means for this design capacity of bolt based on shearing, bearing or tension, whichever capacity is the less governs the design of that bolt or governs the strength of that bolt. We will look at one numerical based on these conditions in our next lecture. We will look at calculations for both single shear joint and double shear joint, and then you will be more clear about these formulae. So we'll meet again soon in our next lecture. Thank you.